Hello, everyone. We're working through statistical methods for rates and proportions, Chapter 6, Comparative Studies, Cross-Sectional, Naturalistic, or Multinomial Sampling. Section 6.6, Approximate Inference for an Odds Ratio, subsection 6.61, Hypothesis Test. So we're going to be working with the same data set about maternal age and the birth weight of the women's babies. We set up our data set and we can look at the joint frequency table. From there, we can get the joint proportions tables and we can get the joint proportions. We can assign P11 through P22 to be the individual proportions. We can assign the marginal proportions P1 dot through P dot 2 by using the apply function. Similarly, we can get the sum of the entire table, the individual frequencies, and the marginal frequencies. We can calculate the estimated odds ratio by considering the odds of A and the odds of not A and taking their ratio. From there, we can think about that first observed cell and remember if the columns added to 25 and the rows added to 40, the biggest that first cell could be would be 25. So we can take X as any values between 0 and 25. All right, if we wanted to, we could say, what if omega was 5? And what we can do is we can walk through the book to calculate each of these individual pieces. And we are going to use equation 6.50 to define A. And we're going to use equation 6.51 to define B. So we set omega to 5, we calculate A and B. All right, we can also set up N11 down to N22 using the formulas 6.52 all the way through 6.55. So we can calculate all of those N's. And then we can calculate capital W, which is 1 over all of those N's. 1 over N11 plus 1 over N12 plus 1 over N22 plus 1 over N21 was the last one that I don't believe I've said yet. All right, so we have all of those values. Remember, those are from equations 6.50 all the way through 6.56. And we can then look at our observed frequencies table. So T observed, that was just our original table T. Then we can look at our expecteds, which are what we just calculated. So the expected frequencies are 14.08, 35.9, and so on. And to calculate the chi-square test statistic, we can take the difference of the observed minus the expected, subtract the continuity correction, and then square those values. We can do that for each of those individual cells, and we get a value of 2.56. And with rounding comparatively to the book, we end up getting 2.544 because we're not rounding the individual pieces, but we know that essentially everything has worked out pretty well. All right, another way to do this hypothesis test is by looking at lambda to be the natural log of omega, and we can calculate the chi-square value according to 6.61. So we're going to get all of those pieces. Note that we can get omega equal to 5, right? And we can look at lambda as the log of W. Just a reminder that in R, the default for the log is a natural log, not base 10. So when I write log W, I'm really saying the natural log of W. So I get a value of 1.61. I can calculate L prime according to equation 6.63. All right. And I can calculate the standard error of L prime according to equation 6.64. All right, so for the chi-square test statistic, we're going to take the observed minus the expected divided by the standard error, and we're going to square it, because essentially here we're looking at a z-score, and then we're taking that z-score, we're squaring it, so we know that it's part of the chi-square distribution. So we're taking our observed L prime minus lambda divided by the standard error of our statistic L prime, and we're squaring it. So our chi-square test statistic in this case is 3.26. And to calculate the p-value, we can use this p chi-square function in R. We have 1 degree of freedom because we have a 2x2 table. Rows minus 1 times columns minus 1 is 1 times 1 equals to 1. And we're setting the lower tail equal to false because we want to get the probability of being as extreme or more extreme. So we're trying to get that upper tail probability in the chi-square distribution. And when we do that, we get a p-value of 0.07. So it's still non-significant, but this just shows you 2 different ways that you can calculate this hypothesis test. So essentially, they make a note in the textbook on page 116 that says the procedure described in the section is more complicated than the one based on the log odds ratio, which is the second one that we just did, but it is more accurate. So if you can use the first way to do the hypothesis test, with very large samples, this is going to matter less and less, but essentially, you have 2 different ways that you can consider doing a hypothesis test on this table. And I hope you learned something, and I will see you on the next video.